So in this diagram here, the protons are red, we'll say. That one is a proton. That one is a neutron. We're just looking at the nucleus. Proton, neutron. And this is a massive nucleus. It has an atomic number very high, okay? If you have a look at this graph here, this table, this graph, along the bottom here is the number of protons increasing from left to right. On the vertical axis, we have number of neutrons increasing from the bottom to the top. Through here, or actually, first this line here represents if the atomic number is equal to the neutron number. So number of protons is equal to the number of neutrons would be that line through there. Okay, you can see this point here. That point there, 70 protons, 70 neutrons. These dots, if you could zoom in close enough, if this had much higher clarity, then you would see that each of the dots there represents a nucleus, and that might be an isotope. It might just be, I think they actually just have the 115 or so, or whatever it was at this time. When this diagram was drawn, there was probably only 110 nuclei that we knew of, and so there's 110 dots there that represent stable nuclei, or where nuclei are reasonably stable. You might notice that it kind of curves towards the neutron side, okay, the y-axis. So what it says is, down here, the number of protons and the number of neutrons are approximately equal. Those people that study chemistry will know that if you have 12 protons in a if you have 6 protons in a carbon nucleus, then you probably have 6 neutrons, and it's reasonably stable. That would be carbon 12. As we go higher, though, we need more neutrons, it seems, to move into this stability curve. So have a look here. Atomic number 40, I don't know what element that is. Atomic number 40 needs approximately, some of these isotopes in here need approximately 50 neutrons to move into this stability area through here. Okay, so this is called the nuclear stability curve. Number of neutrons, number of protons, yes. Yes. And I believe that looks like more than 115. That's probably stable isotopes, or stable isotopes for that nucleus. Okay. What's that, Lachlan? Yes. Yeah. Well, you might know that already if you have a think about it. No, not sure. What we can see here is clearly evident that as the atomic number increases, we need more neutrons. Okay? That's clearly evident. The nucleus needs more neutrons than it does protons, or a higher neutron-proton ratio as we get higher in atomic number. And there's a reason for that. Somebody might already know the reason. Yes, so something to do with the strong force being too short range. That's right, exactly. So we'll go into more detail about that in a second when I get through a couple of other things. Remember, Z is the atomic number. Z greater than or equal to 83, which is bismuth. Bismuth. So this is the atomic number. We see no stable isotopes. What does that mean? That means that any atomic number 83 or greater, the nucleus is going to eject a part of itself in order to move it closer to the stability curve. It says that all nuclei Z greater than or equal to 83 will be radioactive. Clearly obvious on this graph. All, or actually, as the mass of a nucleus increases, we need to have an increased neutron proton ratio to move into the stability curve. T curve. Why does this happen? Somebody mentioned the strong force. The short range strong force. Here's our nucleus again. We know that the strong force is very short range. Is only effective over a few nucleon diameters, not much. Strong force is short range. What is it that wants to blow the nucleus apart? Yeah, that's right. So electrostatic repulsive force, theoretically, I mean, I'll just say it's large compared to the strong force here, but it is theoretically goes on to infinity. But as far as the nucleus is concerned, it acts over a very long distance. So electrostatic repulsion is long range. What's going to happen? As this nucleus gets bigger and bigger, of course, we know the strong force is, well, protons and neutrons are responsible for the strong force. Protons are responsible for the electrostatic repulsion only. And as this nucleus gets bigger, we need to increase the number of neutrons to increase the strong force. As the mass of the nucleus increases, the electrostatic repulsive force which is a long-range force, No, I'm making this a little, whoops, sorry. Takes over, for lack of a better phrase, takes over. And in order for the nucleus to be more stable, it needs more neutrons. Short range, strong force. The extra neutrons increase the distance between protons. Okay. Any questions about that? I think that's reasonably clear. That sort of explains, well, that explains quite well, I think, why we have this nuclear stability curve that errs towards the, or moves towards the neutron side. Okay? You can see here, this isotope of element number 64 in here somewhere needs approximately 90 neutrons. So 64 protons, 90 neutrons. If we go a little bit higher again, let's have a look at 80. Atomic number 80 needs a higher proportion of neutrons again, 120 neutrons compared to 80. Okay, so yes, sorry. Okay. So we have unstable nuclei. They tend to do something what we call decay. If they haven't got the right number of if they haven't got the right neutron to proton ratio, they tend to throw off stuff. They tend to break apart in some way in order to become more stable. And this may not be, we may not have a nucleus like uranium or plutonium that throws off one little alpha particle or beta particle, and we'll talk about those in a second, and all of a sudden is stable and harmless. That's not true. What will often happen is they'll throw off a particle and then they'll still be unstable. And there'll be something else, and then they'll throw off another particle and they'll become a different element again. And then they'll throw something else off because they're still unstable. It goes on and on and on. We call that a decay chain. A decay chain looks something like this. We'll get one. There might be a uranium one here. This is incidentally how they do radioactive dating. I think this is no, this one is here. If it's yes. So here it is. Decay chain. We go from uranium, some isotope of uranium. It becomes thorium, an isotope of thorium. Then it becomes protactinium, whatever that is. Then it becomes actinium. Then it becomes thorium again. Different isotopes, radium. francium. Francium is, for instance, it's the most unstable element there is, apparently, and so that wouldn't last very long at all. That jump. But if we know the proportion or how much uranium was in a rock when it was formed, when it was formed from molten lava or magma, and when it solidified, which we know, which we can find out, and we know what proportion of some isotope is in that rock now, we know approximately how old that rock is by this decay chain here. So uranium doesn't just have one decay, that's an alpha decay there, and a beta minus decay there, and an alpha decay there, and a beta minus decay there, and an alpha decay, and then all of a sudden it becomes stable thorium. It doesn't work like that. Okay. Unstable nuclei. I'll get my picture of a nucleus again. Hopefully it's still there. Yes, it is. This nucleus will throw off stuff. One might be an alpha particle. Does anybody know what an alpha particle is? More commonly? It's a what? Yeah, it's just a helium nucleus, isn't it? Now you all understand this notation now. Mass number, atomic number, or number of nucleons versus the atomic number and just the chemical symbol. You could write that as just like that. That says the same thing. So it's an alpha particle. And it has 2 protons and 2 neutrons. Why the alpha particle? Why is it that it throws off a helium nucleus, do you think? Does anybody know? Why? The helium nucleus has a particularly high binding energy. It's particularly stable, we might say. And so that's why why this nucleus tends to throw off that particle. What do we mean by has a large binding energy? Here's the helium nucleus again. What is the binding energy? And here is the 2 neutrons and the 2 protons. Now, if I have that plus that plus that plus that, the mass of those compared to the mass of this, what's the difference? Does anybody know? This mass is smaller than this mass, the mass of the particles that make it up. So if I add those masses up, I end up with a number that's larger than the mass of this thing. So there's mass missing, which is the binding energy. And that's where Einstein says this, E equals mc squared, energy is mass. Okay. What's the what? The speed of light. The c is speed of light there, yep. Speed of light. Particularly high binding energy for the helium nucleus. What else does this thing throw off? It can throw off, what was that? Ah, okay. You give it all away. I'm supposed to reveal all these one by one. Electrons. So the beta minus particle, beta minus, or an electron, or a beta minus 1, 0. Can be all those things. This is a beta plus, of course, or a positron, or a beta plus particle. Zero mass in the equation. Okay. You can also write this as E minus yeah, electron, and this equals positron. We also have, with each of these emissions, we have gamma radiation. There will be gamma radiation. What's gamma radiation? Electromagnetic radiation or light has the symbol, the funny Y thing, gamma. Particularly high energy. Okay, energy is large. Energy approximately in the millions of electron volts. There's another thing that can happen. What is fission? Yeah. Spontaneous, somebody's got it. Fission, not with a rod and reel. The nucleus can split into two approximately equal nuclei. We call them daughter nuclei, but I'll say that in a second. We'll talk about daughter and parent nuclei in a second. Whoops. Sorry. Can I move on now? Is it? The something we have to add, alpha decay. Alpha decay. Alpha decay just means a helium nucleus has been thrown off of some large nucleus. Happens that the book says happens with an atomic number greater than or equal to 83. And you saw from that decay chain before that we have alpha decay here, and alpha decay here, and alpha decay here, and alpha decay here. But there's beta minus decay that can happen also in there. So there's no real Well, there is rules, things that we have observed with the decay of different nuclei, but there's lots of different types of decay that can happen. There's no rule that it's going to be alpha decay. Beta minus decay. Beta minus decay. Parent nucleus. Now, imagine what is a beta minus particle? Now, you should all know. An electron, thank you. So, please, people, it's starting to get more difficult. If this throws off an electron, what is it lost? Hasn't lost much mass, has it? Lost some charge though, hasn't it? What sort of charge? Negative charge. So what has it got more of now? Yeah, it tends to have a positive net charge because it threw off some negative charge. And this is how I remember it. And don't ask me why. Don't ask any physicist why. A neutron has turned into a proton. That's what we say. Has too many neutrons. A neutron has turned into a proton. Beta plus decay. What do you think? Yeah, parent nucleus. So what's happened inside the nucleus? Has too many protons. And so a proton has turned into a neutron with this positron coming off. We're losing some positive charge. Proton turned neutron. Here's an example of an equation, alpha decay. Now, have I talked about parent and daughter nuclei? Here it is. Parent A, Z. You guys understand this notation at least? Actually, I'll do this in a different color. P denotes parent nucleus. Z, of course, is the atomic number. A is the mass number. Decays. We've known this arrow means a chemical reaction. In this case, we're talking about a nuclear reaction. Decays to form a daughter nucleus plus a helium nucleus, an alpha particle. So this is daughter nucleus. Now, what could I say about the mass number and the atomic number of the daughter nucleus? Knowing the conservation of charge and the conservation of nucleon number. Say it louder. This is going to be A minus 4, and this is going to be Z minus 2. Okay? That's the form of an alpha decay. You must know that there's some gamma emission also as well. We'll talk about that later. That's more complicated. That's where this part of the course gets more difficult. Here's an actual example of an alpha decay. Polonium. Polonium. Something. It's actually lead plus a helium nucleus. What are the numbers here for lead? Yeah. 210 and 82. A minus 4, Z minus 2. Easy. Yeah, that PO is polonium. Polonium, it says polonium decays to become lead or an isotope of lead via alpha decay. That's what that says. Oops. Do we have 2 minutes or 10? I won't start the next part. What's that? Oh, not even, yeah. Thank you.